In this video series, we're going to look at a technique of integration called the substitution method, also known as U substitution, because you end up using a U. And so in the next few video series, we're going to look at different ways of integration other than just saying, here's the antiderivative that we have to gather by, say, undoing the power rule from derivatives or whatnot. And so our goals here are, first to recognize that the function that we're trying to find the antiderivative of is actually found, well, it was found using a chain rule. So if we were a differentiated function, we had to do a chain rule, and then we were trying to reverse that. And then use the substitution rule. And then finally, we're going to use the substitution rule with definite integrals and understand how that changes things geometrically as well. Okay, so as a little warm up here, I have a table that has some functions and their derivatives, and so the first three you just have to differentiate, so that should be old hat, right? And then the other ones you have to find the antiderivative. So I want you to pause the video, try completing these, and resume the video when you're ready to see the solution. So again, the first three should have been rather quick because they're just having to use the chain rule, right? So those are fine. And now going for the last three, here we might need to recognize that this is something like 1 over x squared plus 3 times 2x, and that makes it a little bit more clear what the function the function might be that differentiates to this, and that would just be natural log of x squared plus 3. And then as we're finding the antiderivative, remember that there could have been a constant of integration added on to the end as well. Okay, similar thing here. So again, I might say let's maybe reverse the order, so put the 4x squared at the end, and then we just have to think, well, what differentiates to sine? Well, that would be minus cosine of all this. So I'm trying to undo the chain rule. And then, okay, so then we had to multiply by this, or we had the 4x squared as well. Okay. But if we think carefully about this, the x cubed, right, that would differentiate to 3x squared, and we have a 4 there, so I think what we need to do is multiply this by, well, the 4 would be there, and then for that 3 to go completely out of the integration, I need to multiply that by 1 over 3, right? And then, of course, add a constant of integration. Okay. Next one, so again, we have secant squared tangent, so tangent would differentiate to give us secant, right? And then when we take the derivative of x squared, we would get 2x, not 4x, so it'd be like 2 times 2x, right? So then I think if we think through this carefully enough, I could say that the original function is not tangent like I was thinking. Sorry, I led you down a wrong road there. Actually, what we have to think about is the other way around. So secant differentiates to tangent, right? So if I have something like secant squared of x squared, let's see how that pans out. So secant squared would differentiate to, so I'd have, bring a 2 down, that'd be that 2. And then I'd have, so 2 secant of x squared, and then times the derivative of secant, which would be secant tangent of x squared each. And then I'd have to do the derivative of x squared, so then I think it's actually just this, plus c. Okay, now that one was a bit of a challenge, and we can come back and verify it later on, but the punchline of each one of these is that we had to use the chain rule somehow, right? When going from f to f prime, right, that was just a simple forward application of chain rule. In going in reverse, right, we had to figure out, okay, where was the chain, and are we undoing that chain properly? And so undoing the reversing of the chain rule is a little bit of a challenge, and that's where the technique that we're going to study called the substitution rule comes into play. Okay, and I'm probably going to refer to it as U substitution because, as you can see in the rule, there's a U used to help make the function's representation in the integrand a little bit cleaner. Okay, so we have to have a continuous function f, that's fine. On an interval I could be all real numbers, that's fine. And g is a differentiable function within that range. Okay. and we have little f, which is our continuous function, as the derivative of some big F, which is an antiderivative. Okay, a lot of technical jargon. We just have to make sure that we have f, the outer function, being continuous and g being differentiable. And then what we do is we do a substitution where we let u, this function u, be this inner function, so the input of the composite function, let that be g of x. And then when we differentiate this, so if we look at u is equal to g of x, differentiate that implicitly, we get du is equal to g prime of x dx. And then when we do that, the substitution becomes a little bit cleaner, right? And then we just have to make sure that once we find the antiderivative, right, we have to then end the function in x. We began in x, and in x, so we need to resubstitute. That's going to be the key part that we have to remember. Now, okay, this sounds great in theory. How do we figure out what u is, right? There's a lot of tips and tricks I can give you. I have them sort of listed below here in order of priority in which I would do them. So typically I would try by starting u as a polynomial of the highest degree, or try an exponent on e. If we have a radical, whatever's underneath it. And then most simply, it's the biggest and ugliest thing in the integrand. So notice I said try, right? So for that reason, you may need to try multiple substitutions. It might not work out on your first go around, okay? And also, the other wonky thing is that there could be multiple correct substitutions, or you could do multiple substitutions within the single problem. That could happen, and that is okay. Okay, and so how do we figure out what u is? That's a bit of an art that we will see come up in the examples in the next videos. But the main point is, and I mentioned it earlier when we were going through the rule of the substitution rule, you have to report your answer in terms of the starting variable. Okay, make sure to do that. And with that, we'll end this video, and in the next couple of videos, we'll look at some examples.